Hello, so in this video we're going to look a little bit closer at the Euler equation, kind of where things come from basically. Now if you remember, the reason why we're looking at this Euler equation in the first place is because we want to try and, because it has a singular point, and this is kind of a relatively simple ODE. And actually, if we can look at how this works, okay, look at what happens with this Euler equation, look at what happens here, then we can kind of get a feel and an idea of what happens with kind of at other singular points. Okay, so it has a regular singular point. Where is the singular point? Well, remember, we have to look at the regular singular point in order to find it. We have to look at the first coefficient, so in other words, the p of x one. Okay, so in other words, p of x is equal to x squared. Okay, so then it's going to be a singular point when this is equal to 0. Well, where is it going to be equal to 0? It's going to be equal to 0 at x equals 0. So that's where our regular singular point is. So hopefully you're happy that there is a regular singular point for an Euler equation. All right. Now, how do we go about solving something like this? Well, normally when we have a second order differential equation where these coefficients are constants, where these coefficients in here are constants, okay, then when we solve it in a way like this. So first things first, we turn it into a monic equation. So in other words, I'm just considering the point where a and b are just going to be numbers, okay? So in other words, we just divide through by whatever was here, and we end up with an equation like this, okay? So this is kind of roughly the same thing that we want to do here, except the idea, this is the whole point behind singular points, because when we divide through by this, by this first coefficient, we have to be careful what values we take, okay? Then, because we could end up with singular points. This is the whole idea behind why we're looking at singular points and ordinary points to start off with, because we want to turn it into something that looks like this. We know how to deal with this where we've got just numbers. Okay, so now we want to kind of extend it a little bit further, where suddenly we don't have numbers, where we have variable coefficients, we have functions. Okay, so this is this is the whole point behind what we're doing it, just to reiterate that again. So we first of all turn it into a monic, first or second order differential equation, and then we turn this into a characteristic equation. And the way which we turn it into a characteristic equation is because we guess a solution, and the solution that we guess is y equals e to the rt. Y equals e to the rt. Okay, and then that allows us to we differentiate it again, plug it back into this equation, okay, and when we end up with that, we end up with a little bit of cancellation which happens, so we end up with this. We end up with this equation, okay, and of course you just take out an e to the rt, and that ends up cancelling off because we can divide through by e to the rt, because we know that's not going to be 0. There's no way that's going to be 0. So then basically we end up with this, okay, and this is what's known as the characteristic equation. We go about solving that, and we get two roots out of this. We get R1 and R2, and then we just consider the two different cases, okay, of what the different case of what R1 and R2 could be, okay. But we use this combined with our general solution, and we basically end up with the solution that we're after, okay. And then we basically end up with two solutions. We end up with y1 is equal to e to the r1 times t, and y2 is equal to e to the r2 times t. So these are the solutions that we basically end up with. Okay, that's just kind of a very quick reminder, because we're going to be using exactly or very similar method to this to try and sort of solve this. Okay, well, let's try. If you try y equals e to the rt, it doesn't work. It doesn't work. I mean, not least because our independent variable now is x, okay, no longer t. But basically, if we replace t with x, okay, it's the same kind of process. So in other words, if I just replace t with x over here, so this becomes x, and these two things down here also become x. So just to kind of avoid confusion, okay. But basically, the idea is that we have to basically guess a solution. Okay, so here we had to guess y equals e to the rx, and that worked. Okay, but here if you try e to the rx, it doesn't work. Okay, but let's look, and like I say, it kind of use this for inspiration. Use y equals e to the rx for inspiration. So y equals e to the rx for inspiration. Okay, well, what I'm actually going to do, because this doesn't work, I'm going to use this inspiration, but I'm just going to swap this x and this e. I'm just going to swap this x and this e, okay, and let's see what happens. Okay, so in other words, I end up with x to the power of r. So I'm going to try y equals x to the power of r as my thing which I put in. So if I'm going to put y equals x to the power of r in here, then I need to also put the first derivative in, and also the second derivative of this in. So I need to differentiate it once, and I end up with r x to the power of r minus 1. Yeah, just to get from here to here, I'm just, I'm differentiating with respect to r. I'm differentiating with respect to x, because my general solution will be in terms of x. My y is in terms of x. This y is going to be in terms of x. So therefore, I'm differentiating with respect to x. Okay, and so I've differentiated once to find what goes in here. Okay, and the next thing I need to do is to find what goes in here, so I need to differentiate it again. So I end up with y double dash, just differentiate this. So it's going to be r times r minus 1, bring the power down and reduce the power by 1. Okay, so we end up with this. Okay, then the idea is then I just put this back into my equation like this. So I end up with, well, I've got L of y. Okay, so I'm just literally plugging these things back into here. Okay, so let's have a look at this. So I end up with L of y is equal to x squared times my second derivative. Well, my second derivative is this thing here now. So it's going to be r times r minus 1, lots of x to the r minus 2, okay, plus, so what have I got now? I've got alpha x times my first derivative. Well, my first derivative is going to be this thing here. First derivative is going to be this thing here, so r times x to the power of r minus 1, okay, plus then what have I got left over? I've got plus beta, lots of y, okay, well y is just going to be x to the power of r. Y is just going to be x to the power of r, so let's just call this, let's just call this x to the power of r, just get my colour coding right, so this is x to the power of r, and that's all going to be equal to 0. That's all going to be equal to 0. So all I've literally just done is just plug this back into the equation. Okay, let's just do a little bit of rearranging. I'm just going to ignore this L of y now. I'm not really worried about that. I'm not really interested in that at the moment. Okay, because well, actually, let's just keep the notation up. Before it was L of y. Okay, but I'm actually just going to convenience change this to x to the power of r, because the thing which I've got on the right hand side, I've let y equal x to the power of r. Okay, I've let y equals x to the power of r. So I'm just going to change that to x to the power of r, because I've literally just subbed x to the power of r in the right hand side. I've got nothing involving, I've got no y's written on the right hand side, I've just got x to the power of r's. Okay, so it makes sense to change that notation in there whilst I'm at it. But yeah, like I say, I'm not really going to be too interested in this. I'm just going to be interested and see what happens with this. So let's have a look. Well, I've got x to the power of 2 here, and I've got x to the power of r minus 2. So I've got x to the power of 2 times, because these things are all being multiplied together, times x to the power of r minus 2. Okay, well, I've got the same bases going on, so therefore I can just write, well, this is going to be x to the power of r minus 2 plus 2, because it had x to the power of 2 here. So I've got x to the power of r minus 2 plus 2. They're going to cancel off. I'm just going to be left with x to the power of r. Okay, so that's quite nice. That just cancels down to x to the power of r. Likewise, I can look at this. This is, if you like, x to the power of 1 in here. So I've got x to the power of 1 times x to the power of r minus 1. X to the power of 1 times x to the power of r minus 1. Exactly the same thing is going to happen. Okay, that, I'm just going to add the powers together. So I'm just going to plus 1 here. Minus 1 plus 1, that's going to go to 0. I'm going to be left with x to the power of r here. Hopefully you can see that I end up with nice sort of things going to happen here. So I've got x to the power of r, x to the power of r, x to the power of r. I'm just going to factor that out. So I've got x to the power of r written out the front. Yep. And so now basically this is what I'm left with. Now, providing that x is not equal to 0, okay, I end up with a nice little cancellation which goes off. Okay, providing that x is not equal to 0. So if I make this restriction here, that x is not going to be equal to 0. Now we saw up here that, of course, our singular point is going to be when x equals 0. Well, that's great then, because, providing that x is not equal to 0, then I can just say, basically what I've got here is two things being multiplied together. I've got this thing being multiplied by this thing in the brackets. They're both being multiplied together, and the right-hand side is 0. Okay, so that basically means that one of those two things being multiplied together has to be 0, or both of them has to be 0. Well, providing that x is not equal to 0, then basically this thing on the left-hand side, this x to the power of r, oops, lost my r, x to the power of r can't be 0. Okay, so therefore the only option is that this right-hand side here has got to be 0. Okay, so in other words, what I've got to say is that r times r minus 1 plus alpha times r plus beta is equal to 0. Okay, now that's great. I've got exactly the same thing as I had going on here, where basically I ended up with a cancellation. Originally there was e to the power of r x, I think, here. Okay, and basically there was a cancellation. So same kind of process which is going on here with the Euler equation, just by making the appropriate guess for y equals x to the power of r. Okay, so let's have a look at this thing. Let's just do a little bit of expanding out. So we end up with r times r, which is r squared times r times minus 1, which is minus r. Okay, so let's just do a little bit of factorising going on here. So let's take out an r. So we're left with alpha minus 1. Okay, you can hopefully verify that yourself. Alpha minus 1 plus beta. Okay, so this is what I had before, because I'm not quite sure you'll be able to see that actually. I did that quite quickly. This is what I had before, and I just moved it into that line, just make a little bit of simplification, okay, just by expanding it out and collecting together the like terms. So maybe if I actually just write this r over here, okay, and basically what I'm going to do is I'm going to call this f of r. I'm going to call this f of r, okay, so f of r is going to be equal to that. So if you like the factorised version, or the characteristic equation, if you like, is going to look something like this. This thing here is just a quadratic. Okay, so now if I just get rid of this to make it a little bit simpler, this thing here is just a quadratic, okay, and it's set equal to 0, which means it will have two roots, and the two roots are going to be, so r1 and r2 are going to be given by, so r1 and r2 are going to be given by, well, it's going to be, what's it going to be? It's going to be minus b, so that's b, okay, so minus alpha minus 1, okay, plus or minus the square root of b squared, so that thing again all squared, so alpha minus 1 all squared, minus 4 times a, which is just, of course, just 1, times c, which is beta. So it's going to be minus 4 beta, all over 2 times a. Well, 2 times 1 is just going to be 2, okay? So therefore, in other words, I've got my two roots, okay? Which then means that I'll have which then basically means once I've got these 3 roots, that I can factorise this f of r like this. Let me just try and show you. So I'll end up with f of r, okay, is equal to this thing here, so r squared plus alpha minus 1 times r, okay, plus beta. But I can also simplify this down. So in other words, I'll end up with 2 roots. I can factorise this, because my 2 roots will factorise, into r minus r1 times r minus r2. Now you might say, hang on a minute, are you sure? That is just factorising something, okay? If you're still not convinced, that's just factorising quadratic. If you're still not convinced, okay, let's suppose we have something like x squared, I don't know, plus 6x plus 8, okay, equals 0. Well, if I use the quadratic formula, like I'm using here, if I use the quadratic formula, then basically what I'll end up with is that x is equal to minus b, so minus 6, plus or minus the square root of b squared, so 36, 6 squared is 36, minus 4 times 1 times 8, so minus 4ac, so minus 4 times 1 times 8, so that's minus 32, yeah, minus 32 all over 2 times a, so 2 times 1, okay. And let's just do a little bit of factorising this. This is minus 6 plus or minus, let's just do it in here actually. So what's 36 minus 32? Well, 36 minus 32 is 4. So what's the square root of 4? Well, that's just 2. Okay, so end up with minus 6 plus or minus 2 over 2. Do a little bit of factorising, or a little bit of simplification again. That's over 2 and that's over 2. Break this fraction up into 2. So I'd end up with minus 6 over 2, which of course is minus 3, plus or minus 2 over 2, which is 1. Okay, so in other words, I'll end up with x1 is going to be minus 3 plus 1. So minus 3 plus 1, which is minus 2, okay, and x2 is going to be equal to minus 3 minus 1, which of course is minus 4. Okay, well then if I write that x minus x1, okay, so x minus x1, you'll see why I'm writing this, because you can obviously see it from here. If I then write x minus x1, well then x minus x1 is going to be 2, right? X minus x1 is going to be 2, and x minus x2 is going to be 4. Okay, x minus x2 is going to be 4. Sorry, no, that's not right at all. Sorry, probably just to confuse you there. X minus x1 is x minus this thing. So x minus minus 2. So x minus minus 2. So x minus minus 2 is plus 2. Okay, so that's what x minus minus 2 is equal to. Sorry, yeah. X minus x2 is going to be x minus this thing, so minus 4, which is going to become plus 4. Okay, so this is what I end up with. But look what happens. The reason why I've written this is because look what happens if I just factorise that directly. I can factorise that directly just by saying this is going to be x minus, what's it going to be? X plus 2 times x plus 4. Yeah, equals 0. You can just see just by factorising that directly. I'm looking for two numbers that multiply together to make 8 and add together to make 6. And that's going to be 2 and 4. Okay, so hopefully you can see the correspondence between that and that and that and that. So that is just the reason why I've written my f of r like this, because when I factorise it, I can factorise it like this. Even if it's not nice roots, I can write it like this. Perhaps that was a little bit superfluous, but nevertheless, it's good. Okay, and then just like any quadratic, I can have three cases. Okay, so case number 1 is that r1 is not equal to r2. Okay, case number 2 is when r1 is equal to r2, and case number 3 is when r1 and r2 are both complex. Okay, and I'm going to look at each one of these three cases individually. Okay, and remember that the general solution that I'm after, so I've got, I'm looking for a solution that is of this form, y is equal to x to the power of r. That works, that seems to work. Okay, so then the general solution will be y, so to say y of x, okay, is equal to, y of x equal to c1 times y1 plus c2 times y2, as usual. So it's just going to be c1 times y1 plus c2 times y2. Okay, and I'm going to look at each of these three different cases to tell me what my general solution is going to look like.